All right. So today we are having our last lecture in the first part of the course. The way I see it is we started by discussing very general ideas about how systems with constraints look. We specifically looked at our non-linear systems with constraints based on manipulated equations, solved some inverse dynamics problems. Then we went to linearization last lecture, saw how to do LQR, right? So how to do LQR. And this, for us, have been our journey so far, right? Today we are going to put a final dot on this line where we are going to see how to do observation, right? How to do observation. So as you remember probably from your control theory course, observation comes into question when you don't have access to the full state information, right? It is all fun and games when you have all perfect knowledge about your state, but it is not realistic. Realistic scenario is when you measure some of the state, and some of the state you don't know. So that's where observation comes in, right? And there is a standard way to approach this. That is, we're building what we call observers. You may be familiar with Leuenberger observer, or for example, with Kalman filter. All of those are examples of observers, right? And what happens is you build observer, you would have some estimation of the state information, and then you can do your control, all right? So this is a standard kind of linear control approach. And before we start, let me just point out. So inverse dynamics that we have studied, then LQR, then now observer. All of this kind of gives you a full stack of information, full stack of tools that you can use to control those systems as long as their linear representation is correct, right? And all of this was possible because the way those models behave allows us to linearize and everything, right? Later, we will go towards the effects such as friction and so on, which would break some of the assumptions that we use here, right? But that would be second part of the course. So this is the final one for this part of the course, where we will be able to go as far as we want. So it's we are going to even do this observer step. All right, let us begin. All right. So before we start talking about the observer, we have to do a little bit of a recap. Right. Sorry, I might be slightly slow today because suddenly Zoom interface changed completely, and now I'm not familiar where everything is. So please be patient with me. All right. So a recap. I remember when we talk about linear systems, we are talking about LTI with explicit constraints, right? That is just like a default state. And this is our familiar x dot equals to ax plus pu. That is what we would normally call LTI, right? And here's a part that describes the effect of the constraint. So constraint itself, right? Plus, constraint itself here, plus the reaction forces that make this constraint work. That is kind of like default state. Of course, what we often care about is rather a implicit LTI with implicit constraints, which looks like this. And how this is built? Well, this is built by taking explicit system, substituting basically this part into here, then expressing lambda, then substituting the expression for lambda into the first equation, and that is how you get this thing. That is what I called linear fraction transformation. Right? Now, this is how you get this from this, right? This linear fraction transformation. Nice. And the result would be new A and B matrices, which would be different by this common factor. You can call it a projector if you want, right? So they will be different in terms of this common factor. All right, fine. This is what regards the models. Now let's recap a little bit about the control. So to do control for the system, what we had to do was to introduce new matrices and N, which is a null space of the G matrix. G is, remember, constraint matrix, right? So let me just quickly show it. So it is this constraint. So this matrix G, its null space is obviously where X dot lies. So N is a null space. So base orthonormal basis inside the null space of G. And here we have R, which is a row space basis. So basis in the row space of G, which is the same as saying it is a basis in the column space of G transposed. But yeah, basically it is a row space of G, right? Okay. So those two matrices, and we can decompose X as this sum N times Z plus R times zeta, where Z will be coordinates in the null space of G, and zeta will be coordinates in the row space of G, right? N and R, remember, if you concatenate them together, produce you a full rank matrix because they are orthogonal complements of each other, as null space and row space always are. So together they span the whole space. So they produce a basis, orthonormal basis for the Rn. Okay. Okay. And it is also true that X dot is equal to NZ dot. Why? Because zeta dot, like if you just differentiate this equation here, what you have is X dot equals to NZ dot plus R zeta dot. Okay. N and R are constant because G is constant. Right? So this is constant, so this is constant. Same here. All right. So you would have X dot times NZ dot plus R dot, plus R times zeta dot. Okay. But zeta dot has to be equal to 0. Why? Well, because what? Because we have the expression of the constraints here, right? So Gx dot equal to 0. But if Gx dot is equal to, let me write it out for you. If it is equal to G, oops, is equal to Gn dot Z plus GR dot Z, right? So I use this dot kind of like to imitate LaTeX syntax. So I open up this notation. X dot, as I said, is equal to this like N Z dot plus R zeta dot. Okay. If this is true, we can instantly notice that this part of the expression will always be 0, no matter what, because N is null space of G. So n G times n is equal to 0 by definition. That's just what null space is. Right? But by the same series of definitions, this will never be 0. This will never be 0 unless zeta dot is 0. All right? Because R is in the row space of G. So like this matrix does not have a null space. All right? Z times R does not have a null space. So this matrix would be full column rank. Right? That's what row space is a space of vectors which do map to unique outputs. Right? So there is no null space for GR. That means that for this equation to hold, GR times Z dot equal to 0, for this equation to hold, Z dot has to be equal to 0. That is the only way for this equation to hold. And that's exactly what it is. Z dot would always be 0. There is a much simpler way to think about it, and that is to say, well, this equation here tells me that x lies, x dot lies entirely in the null space of G. Since it lies entirely in the null space of G, what it means is that the component of x that lies in the row space of G is equal to 0. So the projection of z of x onto the row space of G is 0. X dot. And that means that, z dot, which would be equal to R transpose x dot, right? So projection of x onto the row space of G would be equal to 0. So two ways of saying the same thing, right? One that comes from considering equation and realizing that it implies z dot equal to 0, or just substitute and look into the null spaces. And the second way is to say geometrically, say x dot lies in the null space, so projection to the null row space is 0. Therefore, z dot would have to be 0, because if you express it from here, you would get, projection of that's exactly what you would get, like a projection of x dot onto the row space. Right. I understand that probably no matter how many ways I give you to explain this, unless you kind of think about it yourself, it would still sound like gibberish, right? So you have to think about it. So if this doesn't make sense, I would suggest you just work it out with a piece of paper. Just think about it. And if the problem for you is in understanding null spaces and row spaces, that is a perfect moment to do a recap. SVD, the SVD composition, fundamental subspaces, projections, all of those extremely useful. I find that almost everywhere you would be using those. So good time to recap. Okay, so this was that. That is what we call orthogonal coordinates, right? It's an orthogonal method that we're going to use here. Those are like orthogonal coordinates. Okay, next step. We are continuing recap. That is all from the last time. Next step was to multiply the dynamics by n transpose. Okay, that's what we did here and here and here. X, when we multiply by x dot by n transpose, what we get is obviously z dot, right? Okay. No, that's what we get, z dot. You can even reason it from this equation. If you multiply this equation by n transpose, here will be identity because n is orthonormal. You would get this z dot. Like then many ways to prove this. Okay, and at the same time, what we do is we replace x with nz plus rz. That's what we do here. And that is it. That is the way we transfer the model into this orthogonal form, okay, using those orthogonal coordinates. Well, this is a projected dynamics. We could call it like null space dynamics because it lies entirely in the null space of the constraints. So there are many ways to think about it. Okay. Now, LQR can be solved. I'm not going to give you the whole slide as before. You understand that LQR always has a cost function. Then if you want to, you can write a Hamilton-Jacobi-Bellman equation to derive a Riccati equation. And in parallel, you derive cost, the gain. So the two derivations like Riccati and gain. And that's it, right? That's how we derive LQR. So here I'm just going to give you the result. So LQR is basically a recipe how to get a gain for a given cost. So for this cost here, where you have Qn, so Qn is a matrix multiplied by Z on both sides, and R multiplied by U on both sides. For this, you get this recipe. What is this recipe? Well, this is just what I'm trying to say here is that you solve Riccati equation. You solve Riccati equation. Substituting in where you would normally substitute state matrix, you substitute N transpose ACN. Okay. And where you would normally substitute B matrix, you substitute N transpose BC. Where you would normally substitute your U matrix, which is, remember, multiplied by X on both sides. Here you substitute Qn, which is multiplied by Z on both sides. So relation between Qn and Q is obviously will be that it is conjugated by N. Right? Conjugated by N. Like N transpose N, right? All right. So this is a way you solve a Riccati equation. So if you have a solver for your Riccati equation, such as in Python, it will be, I'm struggling to remember exact name, to be something like algebraic Riccati, something like this would be called, right? We usually call it ARE, right? Analytic algebraic Riccati equation. There is also sometimes we say continuous time Riccati equation, so it'll be KER, right? Continuous algebraic, Riccati equation, as opposed to DER, which is discrete time algebraic Riccati equation. There are all of those. All right, so in MATLAB it will be LQR, just be called LQR. And if you solve the Riccati equation, you usually get the variable of the Riccati equation from which you recover the gain. If you solve it, if you solve directly LQR, as in MATLAB, you will get directly the gain. All right, that's I think quite clear. Quite clear. If, by the way, you have any questions about how this works, pause me even right now, and I will describe in detail. I'm perfectly willing to describe like details of technical stuff here. Right. Well, anytime, pause me, and I would explain how this is done, like how we can do it in practice and so on. I think just since it is at the end, like this is pretty much what I've wrote here, is a function call. Like this is not even mathematics. This is directly like what you write in your code, like K equal to LQR, and like all this. This is just a line of code that you have in MATLAB, for example. Because this is like so obvious, I don't want to kind of belabor the point, because like there is very little here to explain. If you are comfortable with what I've got here. But I would, I would like to answer any questions that you have. Okay, so this is how you do LQR for systems with constraints, and this is your cost function that you minimize. Remember, LQR is all about minimizing the cost function, but as a side effect, it also produces a stable system, which, of course, if the system was unstable, then the cost would go to infinity. Okay. Recap over. this is this is the last lecture. This is what we did last time. Okay. Now, let us move towards today's topic. And today, what we have to do is study how observer works. Okay? Study how observer works. So for that, we have to introduce a new line, which is familiar, I guess, for most of us in our LTI formulation. And that is y equal to cx. So y here is an observation output, you can say. C is a measurement matrix, observation matrix, you can call it whichever name you prefer. Notice that here I chose implicit constraint formulation. So I use AC, BC. That doesn't matter. I could have chosen explicit formulation. So I could have chosen A, X, B, U, F, lambda, and G, X dot equal to 0 here, right? Could have done that. That wouldn't change anything because observation is not affected by it in any case, right? So dynamics here, like presence of explicit or implicit constraints here does not affect observation here. So they are quite separate. This is important because it sort of creates a difference between control design and observation design, okay? So normally in the classical control theory, observers are very similar to controllers. So in fact, you can use both LQR to design both. And even the shape of the problem is usually almost identical. And the aspects of doing both of them is also almost identical. They are dual problems, you could say. All right. So this is kind of like the philosophy that you get when you do it for regular systems. However, for systems with constraints, and for quite a lot of other systems where you have you have something that parameter uncertainty, many other things like that. Often what happens is one of those two would have this like new aspect that affects it, like in this case, constraints, and another one would remain kind of like unaffected. There would be imbalance of some kind. And it is important to keep it in mind because there is a difference, like there's a qualitative difference between design observer and controller for those systems. You have to use different mindset, okay? So I will demonstrate it during today's lecture, like the concrete difference. But I want to note for you that it starts directly here, where y equals to cx is not affected by constraints in any way. Okay. All right. By the way, just last one. Remember when we started discussing feedback control, I said it is impossible to do LQR for the feedback controller. For the systems with constraints, because your LQR solver will tell you the system is not stabilizable or the system is not controllable because it has the static states. It has this zeta component, which lies in the row space of G matrix, which does not change. It is static, right? Zeta dot is equal to 0. So it is impossible to control it. All you can do is marginal stability, which LQR is not good at doing. And pole placement, very likely, unless you are very smart at how you're doing it, will tell you it fails to place the poles, right? So that was the problem. Here, I cannot repeat the same for observers, because for all I know, C matrix can be so good that you have observable system. Even though you have static states and everything like that, the system can still be observable. So it's not the same story again. See, not like there is a break of symmetry. Controller, both states and control matrix are affected by constraints. Observation matrix isn't. So I cannot repeat the same arguments here. Okay. So good enough, I guess, as a motivation, so that they are not quite the same. Now, we still have to, usually in practice at least, take advantage of the constraints, of our knowledge of constraints. If we don't take advantage of knowing that there are constraints, what happens is you would estimate the position of your bipedal robot or of your dog robot, okay? So imagine like this is, I'm drawing the dog right now, okay? So here's a dog, 2 legs, okay? Quadruped robot. You will estimate that position without knowing that it touches the ground. You'll be like, but what if my robot actually floats in space like this? What if? This is nonsense. Like, why? Much harder problem. This is a much harder problem to estimate the position of your robot without knowing anything about constraints. Like if you know that both of your feet are actually touching the ground right now, right? And your observation tells you that this 1 foot appears to be a little bit floating, you can use it to correct the observation error, you know? Especially since some of the sensors that you would use would be highly inaccurate. You know, IMU modules compared to encoders are quite inaccurate, especially in some measurements, such as absolute angles. So relying on additional information from the constraints is very nice and very useful. So you have to take advantage of that. It's not just idle kind of like an academic curiosity how to build an observer for the system in a way that takes advantage of the constraints. You have to do it. Otherwise, you are doing solving a much harder problem, which you know maybe you wouldn't be able to solve anyway, right? Okay. Now we start to approach this problem in the exact way as we did before, by multiplying the dynamics by n transpose. So we multiply this equation by n transpose. Here is, let me just this color coded for you to free. So here is x dot multiplied by n transpose, right? Here is AC multiplied by n transpose. Here's B multiplied by n transpose. All right, so this is the first step. Second step is to replace x with the pair z and zeta, right? And you remember that x is equal to nz, rz. So nz, rz, x, nz, rz. So we substitute this pair into each place where x is. So here, right? And we get these guys. Okay. Well, this is the same step that we did before. Well, mathematics didn't change, but notice that we also do it in the observation, of course. We want to change variables, so we do it there. Okay. Now what we do is what I would call subspace representation. So we write the same dynamics as before. And let me show you that it is the same dynamics. So I'll go one slide before. Let's go step by step. So z dot equals to NANZ plus NARZ plus NBU, Okay, this is NAN zeta, NAR, sorry, NAN z, NAR zeta, and BU. Now here, same equation, z equal to NAN z, NAR zeta, and BU. Same exact dynamics. Same exact dynamics. So nothing changed. I just brought it as a matrix. Now, though, I add additional column which says that zeta dot is equal to 0 times z, 0 times zeta plus 0. So just 0. Right? I just duplicated the 0 until I filled up the whole row. Why did I do this? Why did I do this? Well, you will see this part will become extremely useful when we design observer. Okay? It is true also. And since we have a new pair of variables, it is nice to write the dynamics in terms of this pair. Of course, we didn't have to write the second equation because it's just 0 equals 0. But, it is also not wrong. It's also not wrong. Okay, observation becomes looks like this now. Please notice this pattern. There are a few patterns here. So first, there's a block AN and AR. Those blocks we already saw them before. Okay. Then there is this block NR times ZZ, which would appear every time we do observations. Because essentially what we did here is just we replaced X by this whole thing. Like this thing is just X. So X is equal to Z and Z plus RZ. So this block will appear again and again and again. So it is nice to can notice it. Okay, otherwise quite simple. Well, this is, why do I call it subspace representation? Well, because basically it is the same as before, same as X, but we broke it into two individual subspaces. So there is a Z subspace which has motion in it. Z moves around. Okay. I guess let me even do it more carefully. So there is this Z representation. Right. There's a motion. Okay. And then there is a static zeta component, which does not have any motion in it, right? And you even have this like situation where X, it depends on zeta in a way, right? So you have this block which in the Z dynamics depends on zeta. And of course, if you want to be pedantic, you can say that there is a 0 which depends on Z and the downstairs. Right, so you have this like decomposition basically into two orthogonal variables. Whereas in X, it was all mixed. Like you couldn't tell which part was depending on which. Definitely not in terms of columns or rows. Okay, so subspace representation. We basically decomposed it into null space and row space. Okay. Now, next stage is to propose an observer. So I would like you to look into it for a second and see if you find it familiar. See if you find it familiar. Essentially, this is a Leuenberger. This is a Leuenberger observer. So what makes an observer a Leuenberger observer? Well, first, it would have to have the same state matrix as the original system, right? Multiplied by observation variables, right? Okay. So those are estimates of the state variables, right? It will have to have the same control times, control matrix times control. There is no estimates here. It is the exact value because control is supposed to be known exactly. Right? In addition, it has this interesting appendix where you have gain of the observer, times the difference between actual y, which is read from the sensors, like output y, and the y which you get from your observation. Okay. So we have the difference between y that you actually read from your sensors and the y which you estimate from your observer, right? Like if, let me put it like this. If this was a true estimate of the, so correct estimate of the state variable, then this and this, the difference would be 0, right? That would be exactly, the difference would be exactly 0. And multiplied by any matrix, you still have 0. So this whole thing would just be, imitation of the dynamics, like perfect imitation without any error. But since usually it is not so rosy, right? The picture is not so nice. You have a discrepancy between this and this. This discrepancy is observation error. We multiply it by L, like observer gains, and we correct our dynamics here, which depends basically on it imitates the system that we observe, and we correct it a little bit. So this is what makes a Leuenberger. Leuenberger imitates the dynamics and has this additional linear control, a linear gain. Okay, all right. So z hat and zeta hat are estimates of z and zeta. Okay, so this is the observer. Now let me point out, just in case it was a while before, since you saw it last time, just a few obvious things. First of all, this is already the recipe of how to do it, right? This is more or less half of the work for observer design. So when you're going to actually implement this in practice, so let's say you're building a robot, you want to implement it in practice. This, what I just showed you in color, is what you're going to actually build. So your code will contain, and here I'm oversimplifying a little bit, but hopefully you'll forgive me. It will contain those, z dot, zeta dot. It will be discretized, of course, right? And it will contain the state matrix times the actual state variables here. You would add this guy, and you would add this guy. So all of this would be in your code. It will be run in your code. So this is not just a mathematical entity. It is also what you're going to write. Okay. Just as with control law, you would have a line u equals to kx. Here you would have like all of this stuff. Okay, of course, in your case, to be discrete, most likely, right? How you go from continuous to discrete, that is a separate question, which we'll leave it for another day. But of course, you know how to do it. The simplest way is by a finite difference approximation of a derivative. So, in a pinch you could do it, I guess. All right. Now, the remaining question, this is all cool and nice, but this is not the full picture. The remaining question is how to get L. Everything else is clear. There is no problem with, you can write it as a code, easy, no issues. How do we get L though? That is not clear. We don't have an answer to that yet. That is what we're going to discuss right now. Okay, so here's a theorem. Here's a theorem. So orthogonal observer, so what we saw before, orthogonal observer and with this associated, implicit constraint LTI, with this special control law, which is designed like this, minus kz times estimate of z, minus k zeta times estimate of zeta, would form a stable system if the following conditions are satisfied. Right? If the following conditions are satisfied. And the conditions are here. Conditions are here. So let's first understand the conditions. It is written in a very compact way, and I like to keep this compact way if possible, but it doesn't have to be. It does we could write it out, I guess. Well, let's understand this. This is essentially what we have here is the stacked transposes of those matrices. So if we define the matrix E, which is M R, so null space and row space, so it will be a matrix that is a basis in the ambient space, right? So it's a basis matrix that is a basis the ambient space in Rn. This would be just E transposed here. Okay. This will be just E transposed. All right, so that's it. That's just E transposed. Now, what happens here? What happens here? There's different color. This is AC transpose M. So for some reason, we transpose matrix A multiplied by N. Here's just 0. Okay. Minus observation matrix C transposed, L transposed. Okay. So this looks a little bit mysterious, like because we have this, matrix, 2 stories here, brackets. We have another 2-story matrix here. The dimensions are not clear, and here's the 1-story matrix. So, like visually, it is a little bit confusing. But this is the cost we pay for it being compact. We could have written it bigger, then it would be clearer. For example, let us just open up this expression a little bit to see what happens. So if we open up this expression, and let me point out what exactly we are opening. So I'm trying to open this guy, okay? So what I put in the square. If we open it, we would be multiplying basically this like square matrix. This green matrix is square, okay? Because E is square, E transpose is square. So it's a square matrix. We're multiplying it by this guy here, which has, in terms of its, let's understand the dimensions, I guess, of this guy. I just spent a little bit of time understanding the dimensions of this guy. So it can be, this guy has the same number of columns as N. So let's say, and N has the same number of columns as the null space of G. So let's define this as, I guess, like K. So K is a dimension of the null space of G. Okay. K is a good dimension of null space of G. Okay, until it's less than N. Right. This is green matrix is N by N. So this blue matrix is number of columns is K, because there is N here on the right hand side. So we already know that dimensions of the column, number of columns is N by K, K. What is the number of rows? Well, we can already say it would be n because it is multiplied by green matrix, or because we have a C transposed here, okay? And C transposed would be n by something matrix. Something depends on dimensions of y, right? C is y, like something by n. If we transpose it, will be n by something. Okay. So this matrix here is n by k, n by k. It has n rows, k columns. So there's a tall matrix. It's a tall matrix. Okay. Nice. We have a tall matrix multiplying a square matrix. So it becomes already less mysterious. If we open it up, what we have is we'll multiply the first. We'll first multiply this n here. So we'll get this like n transpose AC n. That's what we get. That is the first row. And downstairs we would get R transpose AC n. All right. So this is what we will get after multiplication. All right. So after multiplication, that's what we're going to get. So you can see already this is quite familiar, right? Those two blocks are quite familiar. Okay. Let me just double check that's correct. I didn't mess up anything. Okay. All right. It should be correct. It should all be correct. But if if you find any mistake in any of this, let me know. All of this should be correct. All of this was double checked, like many things. All right. And what about this part? What about this part? So we just checked this. All right. It's notation is a little bit weird, but ultimately it is just a square matrix multiplied by a tall matrix. Everything fine. So what about this guy? Well, this guy times this guy, we already saw this, right? We already saw this. We just saw it in a transposed form. So if we transpose all of this, what we would see is L times C times NR. That is what we saw in previous slide here. L, C, and R. Okay. So this multiplication makes perfect sense. It is exactly what we saw before. With this too, if we transpose this multiplication, what we would get is basically this row, right? So you don't have to follow all that I said. Like you don't have to try to go through those steps. What I was trying to do is to just explain that this expression here mathematically is perfectly sensible. The notation is strange because of the visual sizes of those matrices. But when you perform multiplication, it becomes quite normal. Like you see basically what you saw on the previous slide. Okay, now the key term, I guess, is this one. What does it mean? Well, as before, it means Hurwitz. This matrix has to be Hurwitz. So this matrix for the observer and the system, LTI system, to be stable, for those to be stable together, this matrix has to be Hurwitz. All right. Moreover, not only this matrix has to be Hurwitz, but those two, well, let me now use a different color. Those two KZ and KZ has to be chosen such that KZ has to be chosen such that this matrix is Hurwitz, which is true if we used LQR that I described previously. So this condition 10 basically is equivalent to doing LQR the way we prescribed in the second slide, right? And K zeta is just chosen like this. Why like this? Well, it is basically to cancel this free side. This has nothing to do with stability. This is more to make sure that the system converges to 0 instead of converging somewhere. If we want convergence towards 0, this is how we choose KZ. We could have chosen it in a different way. Then we would converge somewhere else. All right. So this is expression 11 is just to make sure that we converge towards 0. Okay. So this so far, you can see it as a recipe. And we'll go back to it in a bit to, I guess let's do it right now. Let's do it right now. So I said that this is the recipe of how to do it. Well, can we actually use it? Well, yes, we can. We can use it with LQR. How is it done? Well, here is your state matrix, right? This guy times this guy. This is your state matrix. This is your A. Okay, this is your A. Now, here is your control matrix, which is this times this. This is your B. Okay. And Q and R would be, Q would be, in this case, a matrix multiplied by the pair Z and zeta. Okay. Actually, the cost will be in terms of observation error, but we'll see it in the next slide. And the R will be in terms of effort of observer. I delegated to normal LQR. Normal Leonberger observer. How we use LQR to tune it. There is this whole talk about dual systems, etc. So delegate to that. But for if we want to go into details of how to design cost function and so on for observer, we can have a discussion here. I don't mind. It's just that I don't want to insist on this because I'm not sure if you are interested. Okay. So this yellow matrix is your B matrix. So you just get your A matrix, B matrix, Q and R, plug them into your Riccati or into your LQR, and you get your gain matrix. The gain matrix you'll get is this guy, of course. Is L transposed. And as usual, you just transpose it to get L, and that's it. So this is already actionable. Like equation 9 is directly a recipe of how to do LQR. It is written in this strange way, but it's not so strange once you think about it for a bit. Okay? Like same here, there's your state matrix. Here's your B matrix. You plug both of them into your LQR. You get your gain matrix. That's it. Right? So this is what we did in the previous slide. Okay. All right. Now, all of this said, let's try to find out where this came from. Like, this is nice, but this is clearly some shenanigans going on. This is not a standard Leonberger stuff. Like, you don't find this in the textbook, basically, what I'm trying to say. So let's try to understand where this comes from. Okay, I mean, without such understanding, it is dangerous to use tools of this kind. Okay, so let's try. So, and it is actually not very difficult. It's not very tough to understand. So first of all, we define observation error, which is the difference between Z and Z estimate, okay, and zeta and zeta estimate. Okay. So just the difference between those two defines our estimation error. Okay, so E will be our estimation error. Okay, and we would aim to rewrite find the dynamics of the estimation error. How do we find dynamics of estimation error? Well, basically, we differentiate this expression. So E dot would be equal to Z dot minus Z dot, Z hat dot, zeta dot, zeta hat dot. Okay? So just differentiate this. What it means in practice is we take this expression minus this expression. Right? So we subtract the second from the first. Okay. What are those? Remember, this was our dynamics in the subspace representation. Okay. And this was our observer, our Leuenberger observer. So those two we saw on the slides. I just copied them here. And now what we have to do is we have to subtract. It is quite easy to lose ourselves in this subtraction. Remember, we are going to get this minus this. Okay. But it is not so hard. It's not so hard. So let me show you. Let me show you. First of all, this guy here minus this guy here is 0 because they are exactly the same. So this is going to go away. This is going to go away. Good, nice. Second, we have exact same expression here and here. So when we subtract, we just get vectors, z minus vectors z hat, zeta minus zeta hat. So this matrix will take it out of the brackets, and in the brackets we will basically have this. So what we get is E in front of this matrix, right? Like it's quite simple. Like matrix doesn't change, just get E in front of this matrix. This part, like those two steps that we just performed, canceling of control and getting E in front of the state matrix, this is essence of Leuenberger. Leuenberger is designed to have this result. If we chose some other observer, this step wouldn't be possible. But Leuenberger is specifically designed to allow this stuff that we see. Okay, all right. Now, last step is to do something about this. And what we do about this is very simple. We notice that Y can be opened in the exact same way as this, right? They are the same, except Y would have true values of Z and Zeta, whereas this would have estimated values of Z and Zeta. So this whole green matrix times lambda, times L, would go here. And it would be taken out of the brackets. And in the brackets, we would again have this, which would be E. So Leuenberger observer error dynamics, so observation error dynamics, is always this nice expression, like something in the brackets times E. Let me point out critical fact here. It is absolutely like very important, very critical if you're going to do it yourself, if you're going to design it yourself. E dot depends only on E. It does not depend on either Z or Z hat, zeta, zeta hat. In normal Leuenberger, it wouldn't be depending on X or X hat. It only depends on E. Of course, you can say E depends on those variables, but that would be missing the point. The point is that you can write in this new variable E the dynamics as an autonomous system. And not only autonomous, but autonomous in the sense of not depending on other variables. Okay. So the dynamics of this error depends only on itself. That is, T is a crucial component. Okay. Good. we got that. This is just a simple step of deriving this aerodynamics. We have to do it, and we have done it. Okay. Now we could like I don't know, looking here is nice. Okay, but we have our z, like our dynamics of our original variable, like z. Okay, specifically z has a dynamics. Like zeta doesn't have a dynamics, but z has. So z also depends on itself, of course, right? Once we substitute control law, we find that kz depends on z. I guess here I should have maybe written it out a little bit more. So let me just write it here. U is equal to kz, remember, times kz times z hat. Okay, not z, z hat. So it would be with a minus sign, of course, and minus, you know, k zeta, zeta hat. Right. Good. Because when we are going to use it, we are going to actually use those estimates. We don't have estimation error. Like estimation error is not variables that we can use in our code, because if we knew it, we would always be able to set to 0, right? Estimation error is not available to us, but in mathematics it is available, right? So this hat, zeta hat, right, is a relay. Remember, we say that z minus zeta hat is equal to e. Yes, ez. So this means that zeta hat would be equal to e z minus e. Z minus e. Right? Yes, z minus e. So when we take this control law, what we actually do is instead of this guy here, we put this guy here. And that is how we have here this part, like kz times z, okay? Kz times z. It is from here, here, here. And this is why also we would have a separate component kz times e, right? Times e. We would have a separate component. Why we would have this is because when we replaced zeta hat, we got two variables, z and e. Yeah? And this e component would arrive in this form here, ke. Ke I define as kz, and kz are concatenated. Okay. So this component has to do with this part. And notice the sign changed, right? It was minus, there's a plus here. And here we have this whole huge section which depends on zeta, which is static. This part does not influence stability, it is static. And here you can see, remember we had this short discussion of how to choose k zeta? Well, now you see what it influences. Like if this whole thing is equal to 0, so you can choose k zeta such that this whole part is equal to 0. Good for you. It cancels. If it's not 0, well, you would have a static component here, which would influence the final steady state value of z. Okay. We propose to choose k zeta such that this component goes to 0. That was the idea. Okay. So in short, second step. So the first step was aerodynamics of the Lemberger observer. Okay. Second step, rewrite the dynamics of the system in such a way that it will be a function of new variables. first is the original variable, right? And second is the observation error. We cannot leave the dynamics to be if what naturally is a function of state variable and estimation variable, so z hat. We cannot leave it as a function of z hat because that we want to get rid of z hat and replace it with estimation error. This is important for the next steps that we're going to do. So the first step is, again, find dynamics of E, estimation error, which is always depending only on itself. And second is dynamics, which would depend on both of them, on the state and estimation error. Okay, this was the second step. Now to the last step. Last step is to write them together. When we write them together, what we have is, here is a description of the dynamics, right? So let me show. Z dot equals to this guy times Z. So this is what depends on, like, state variable depending on itself, right? Here we have the components of the state dynamics, which depends on estimation error. We saw it on the previous slide. And here separately, we have estimation error dynamics, which depends only on itself. Okay. Depends only on itself. Good. So that is it. That's what we have. I used here some short, like small annotation, like n bar, which is like n with 0 section, E, which is n concatenated with R. Ultimately, this is just to make sure that we can write it in this nice form. Yeah, you can open this up and test that everything that I wrote here is correct. Now, this is done. And now we have a key observation, which is a linchpin of our Leuenberger observer design and many other things that we do in control. And that is the fact that this matrix is upper block diagonal, oh, sorry, triangle, upper block triangle. So it has a block here, it has a block here, and most importantly, it has zeros here. So because it is upper block triangle, the eigenvalues of the sum of the total system, or the system overall, depends on eigenvalues of the block on the diagonal. So we don't have to compute eigenvalues of the total system. We only have to compute eigenvalues of the blocks. It is a key observation. It's very important. It allows us to separate control design from observer design. Why do I say it allows us to separate control design from observer design? Notice controller KZ appears only in the orange block. Notice that observer variable L appears only in the observer block. So because we could eigenvalues of the total system depends on those two blocks, we can separately define KZ that makes the eigenvalues of the orange block negative Hurwitz, right? And eigenvalue separately find L that makes eigenvalues of the green block Hurwitz. Okay. Nice. This is constant. This is stuff that depends on zeta. Okay. It should be 0 if we chose KZ. Well, but it's like a separate issue. You don't have to discuss it. It should tend to 0. That's a more correct way to say it. All right. So what do we have here? What do we have here? We have here is what we call a separation principle. Separation principle. It is exactly the same as in classical control, where you do pretty much the same stuff. It's just the blocks are a little bit smaller because we don't have all those endless N and R's. Okay, those blocks are slightly smaller and prettier. Okay, but ultimately it's the same. The whole process is kind of the same. This means we can do LQR on the orange block, LQR on the green block. for example. And finally, if you notice this block here, if you transpose it, it will be E transpose times, A transpose N, C transpose L transpose, right? And this is exactly what we saw in the theorem. E transpose ACN, E transpose C transpose L transpose. This matrix here is like has a zero, right, downstairs. This is the same exactly the same as this matrix, because of just notation is more nicer in this last one, because we have N bar which has zeros here. Okay. So that is we managed to hide this zero in this nice bar that we put on top. Oh yeah, it is exactly the same. So this is the proof of the theorem. This is the proof of the theorem. The reason I show you this proof is, first of all, I don't think it is meaningful to apply Leuenberger without understanding separation principle. Because if you apply it again, one day you would apply it to something that does not have a separation. So, for example, you can apply it accidentally to a robust case when you have parametric uncertainty. Parametric uncertainty breaks separation principle for very good reasons, which you would understand as soon as you try to follow all of those steps to arrive to the same separation principle. But with parametric uncertainty, what you would notice is that there is no zero block here. And this breaks your ability to use observer, like separate from controller. You have to design them at the same time. And you arrive at robust observer design, robust Leuenberger observer design, which is a separate, quite important issue. Or you arrive to dynamic output feedback, which is as opposed to static output feedback, which is what you studied in all your introductory courses, including this one. All of this was static output feedback. Static in the sense that this observer, yes, what would be a good way to describe what I'm trying to say? Dynamic output feedback is the generalization of Leuenberger, where you have 4 matrices to tune instead of 1. Okay, Leuenberger plus controller is effectively dynamic output feedback. It's just a particular case. Static output feedback is just LQR with full X information. Okay. So you would arrive to all those territories, but if you use Leuenberger without understanding separation principle and where it comes from, you may accidentally not arrive there, but instead arrive to an error. And it is okay if the error leads to like low marks on the exam. It is not okay if the error leads to like 8 more months of the development of your project, where you are like a principal engineer and you are designing, nothing works. And then you realize that you were using a theorem without understanding the derivation. And that's why you were pushing for endless development without catching the error. And the error was that the theorem didn't apply. You had to use a different theorem. So it's like, you're getting closer to this real life stuff. So I suggest, don't forget theorems. Theorems were not for exercise. They were not for fun. They are actually extremely useful. So, and stuff like separation principle, 3 pages, you saw how fast we derived it. So if you're going to use observers, you have to be able to do step 1, step 2, step 3. Okay, that's I strongly suggest that this is a prerequisite, even for purely engineering stuff. Okay, so this is it for how to design observer for systems with constraints. We don't have a lot of time, so I will just wrap up. This is the paper that I based this lecture on. You can see that, I have a natural bias. This is my paper with my very good colleagues used to be from our university. So it was a pleasure to work with them. In the paper, if you read it, you would find that I only showed you one section, and regarding observer design, there is like 3 sections that I skipped, which would all tell you about how to use less observations. So how to modify in this design this one matrix here, how to modify it to have less columns. Having less columns, it would make it more easy for this whole system to be observable. This you would see, so this you would see because it's like dimensionality of the system shrinks, while this remains the same. So it will have more chances to be observable. Okay. And there is like a whole number of sections on that. This is of practical importance for most working robots. There is like this direct application with observer without taking advantage of the fact that you can shrink R would not lead to good results. Okay, so you have to follow additional steps from the paper to choose a better basis in R. And this has to do with the fact that some of the states are obviously always 0, so you don't have to actually go through all the steps here. You can just clear them out of your equations, like velocities associated with the contact are always 0, right? And it can be done automatically. In the paper, you just have direct recipes, which are like one-liners. They're very simple. So, yeah, if you were interested, you can read the paper and you would see all this information there. Okay, so this is it for this part of the course. This was kind of like developed into a linear algebra course, a linear control course. Next, we will go into like friction and other things which will get us closer to practical stuff that people do with quadrupeds. Please don't leave the call for a second. I will just get a little bit of like housekeeping announcements.